Good afternoon to everyone. My name is Revinod. I am from CAC section. Today I am saying a topic about Hamiltonian cycle detection in space graphs. A graphs a probabilistic approach. First of all, let me say an introduction about Hamilton cycle detection in space graphs. Hamilton cycle is a path that visits each vertex exactly once and its starting vertex. Mainly in Hamiltonian path, there are necessary rules. End vertex and starting vertex should be same. In sparse graphs, traditional algorithms may struggle due to the lack of edges connecting vertices. Understanding sparse graphs. Sparse graphs have relatively few edges compared to the maximum possible edges. Detecting Hamiltonian cycles in sparse graphs is challenging due to the limited connectivity between vertices. Probabilistic approaches offer a promising solution to efficiently identify Hamiltonian cycles in sparse graphs. Probabilistic algorithms. Probabilistic algorithms use randomness to efficiently solve computational problems. These algorithms provide a probabilistic guarantee of correctness, often with a trade-off in terms of certainty. By leveraging randomness, probabilistic algorithms can explore a wider range of possibilities in sparse graphs. Probabilistic algorithms. A probabilistic algorithm is an algorithm designed due to the use of outcome of a random process. Example, flip a coin. How can making a decision by flipping a coin ever be better than actually calculating or even estimating the best choice in a particular situation? Importance of Hamiltonian cycles. Hamiltonian path is a path in a graph that visits each vertex exactly once. Hamiltonian cycle is a cycle in a graph that visits each vertex exactly once. Hamiltonian path or cycle problem determining if Hamiltonian path or cycle exists. Hamiltonian cycles have various applications in optimization, scheduling, and network design. Detecting Hamiltonian cycles in sparse graphs can help identify efficient routes or circuits in real-world scenarios. The presence or absence of a Hamiltonian cycle can provide valuable insights into the structure of a graph. Challenges in sparse graphs. Sparse graphs pose challenges for traditional deterministic algorithms which may struggle to find Hamiltonian cycles efficiently. The sparsity of connections between vertices complicates the exploration process required to identify a Hamiltonian cycle. Probabilistic approaches offer a more flexible and scalable solution to tackle the complexity of sparse graphs. In the above diagram, you can see the challenges in sparse graphs. If is it directed, and when it is undirected. Probabilistic strategies. Probabilistic strategies in Hamiltonian cycle detection involve randomization to explore different paths in the graph. By introducing randomness, these strategies can efficiently navigate sparse graphs to identify potential Hamiltonian cycles. The probabilistic nature of these algorithms allows for a more dynamic and adaptable approach to solving the problem. Monte Carlo method. Monte Carlo method is a common probabilistic approach used in Hamiltonian cycle detection. The Monte Carlo method can be used in finding Hamiltonian cycles by generating random paths and checking if they satisfy the necessary conditions for a Hamiltonian cycle. It's a probabilistic algorithm, meaning it might not always find a solution, but it's efficient for large graphs. Would you like more? If suppose example, you see in the above diagram, if it is 10 samples or it is 50 samples and 100 samples, and when it is 1000 samples. The Monte Carlo method can be used in the context of Hamiltonian cycles by randomly generating potential cycles and checking if they satisfy the Hamiltonian cycle criteria. This approach can provide an estimate of the probability of finding a Hamiltonian cycle in a given graph. This method involves randomly sampling paths in the graph to ascertain the presence of a Hamiltonian cycle. While not always deterministic, the Monte Carlo method provides a quick and scalable way to identify potential Hamiltonian cycles. And it is applied to the Hamiltonian cycle problem by using random sampling to explore potential solutions. It involves randomly generating permutations of vertices and checking if each permutation forms a Hamiltonian cycle. While it's not guaranteed to find the optimal solution, it's useful for approximate solutions in cases where finding an exact solution. The Monte Carlo method in the context of the Hamiltonian cycle problems involves using random sampling to approximate the solution. In the case, you randomly generate potential Hamiltonian cycles and evaluate whether each one satisfy the necessary conditions. While it's not guaranteed to find the optimal solution, it can provide good estimates, especially for large instances where exact algorithms may be impractical. And the next one is Las Vegas algorithm. Las Vegas algorithm is another probabilistic approach that focuses on finding a Hamiltonian cycle with a high probability of correctness. By combining randomization with efficient exploration strategies, the Las Vegas algorithm can effectively detect Hamiltonian cycles in space graphs. A Las Vegas algorithm, unlike Monte Carlo, guarantee correctness but not necessarily efficiency in the context of the Hamiltonian cycle problem. A Las Vegas algorithm would continue to search until it finds a Hamiltonian cycle or proves that one doesn't exist. It may take longer to run compared to Monte Carlo, but it ensures while the algorithm's runtime may vary, it offers a reliable probabilistic guarantee of correctness. The Las Vegas algorithm is a probabilistic algorithm that always gives the correct result but may vary in this runtime. Unlike the deterministic algorithms that always produce the same output for a given input, Las Vegas algorithms can produce different running times depending on chance. However, they guarantee that if they terminate, they return the correct result. It's named after the city of Las Vegas because of its elements of chance. Right, performance and trade-offs. Probabilistic approaches in Hamiltonian cycle detection trade-off certainty for efficiency and scalability. While traditional deterministic algorithms guarantee correctness, they may struggle in sparse graphs due to the limited connectivity. But probabilistic algorithms provide a more dynamic and flexible solution that can adapt to the challenges of sparse graphs. And finally, conclusion. Hamiltonian cycle detection in sparse graphs, a probabilistic approach offers a promising solution to the challenges caused by spacecrafts. Probabilistic algorithms leverage randomness to efficiently explore spacecrafts and identify potential Hamiltonian cycles. By embracing probabilistic strategies, researchers and practitioners can tackle the complexity of spacecrafts and uncover valuable insights through Hamiltonian cycle prediction. And thank you.